Hello and welcome to another wonderful adventure of the New York City Category Theory Seminar. Today we are hearing from Bruno Gavranović, categorical deep learning.
Gavranović, yes.
Sorry. Categorical deep learning and algebraic theory of architectures. Take it away, Bruno.
Thanks very much for inviting me, Nathan. It's great to be here. It's great to share some of this research, some of this work. Uh, the comic you see here is an XKCD comic. I've been using this for my talks, on occasion for the last 5 years or so. And if anything, it's only more and more relevant.
Bruno, you're stuck. Hello? Okay.
So I was saying I like this comic because today it's more relevant than ever. I've been using it for the last 5 years, and if this is how you think of machine learning, coming from category theory, you would be absolutely right. Uh, so today I will tell you a little bit about how we're aiming to change the status quo, um, and I'll tell you about categorical deep learning and algebraic theory of architectures. Uh, this is based on the eponymous paper that was joint work with a bunch of other people. So this is Paul, my colleague from Symbolica, and a number of other people from Google DeepMind. So that's Andrew, Tamara, Joao, and Petar. Before I continue, do you still hear me?
Perfectly. Go.
Perfectly. Fantastic. Great. I'm just checking. So one disclaimer, the target of this paper is a machine learning audience. So if you end up perusing it, you will see that we are really trying to bring category theory closer to deep learning and emphasize the theory as a tool for a lot of the problems in deep learning. So as a result, by the standards of this seminar, the category theory you will find in the paper is very simple. There is categories, at most 2 categories, but nothing too fancy. This paper was submitted to this year's machine learning international conference on machine learning, and it got accepted. So you can see us here in Vienna spreading the gospel. Funnily enough, I think this was the only paper that had any commutative diagrams. I think I've seen maybe one other out of like 2,000 posters. So it's still a very small and niche community. But why I'm saying this, it's because today the target for this talk is a category theory audience. So I'm going to slightly modify what we're talking about and give you a slightly different perspective. So the plan here is to bring machine learning closer to a category theory audience and emphasize what I think is a striking application of category theory. And really emphasize what I think is a large opportunity space in deep learning for application of structural methods. As this is a category theory audience, and checking one more time, am I still on?
Yes, perfectly. Go.
Perfect. Perfectly. I need to add a disclaimer on how to read the title. We haven't had problems with machine learning audience, but we realized that algebraic theory here has a particular meaning. So the intended reading of the title is categorical deep learning is an algebraic theory of all architectures. This is meant to distance it from, say, geometric deep learning and more geometrical methods, more geometrical theories such as topological deep learning. So we are really focusing on algebraic structure, and not in the sense algebraic theory in the sense of Lavier. Coming from category theory, deep learning might seem a little bit ad hoc, but as I've said, the fact that a lot of the math is ad hoc does not mean that the field is devoid of deep insights and what I think is really just novel mathematics, novel things we can find and use. So that's I will argue this in this talk. All right, so if you're here for 2 minutes and you have to leave, what's one slide summary of the paper? It is that we provide formal specifications of neural network architecture that subsume existing equivariant approaches based on geometric deep learning, but also cover recursive and branching computations. That's it. Why is this important? Well, there's many reasons. And just very briefly, I mean, everyone sees that AI systems are being scaled and they're impacting almost every aspect of our lives today and are inducing a really transformative change to society. So we're really scaling these things without a rigorous understanding of these internals. So our aim and goal is to make a step forward and furthermore help design novel architectures inspired by these structural principles, architectures which we have a better grasp on internals, better grip, better understanding, better guarantees. So having said that, this is the plan for today. I'll talk briefly about what deep learning really is. I'll talk about geometric deep learning, which in many ways is a precursor to categorical deep learning. And then I'll tell you what we've done in the paper and some next steps. Are there any questions or thoughts before I start? Any comments, or should I just go on?
Any questions? Okay, so go on. It sounds interesting.
Let's go. So there's many ways to introduce the field of deep learning. One way I'm introducing it here is as the science and engineering of writing programs that find structure in unstructured data. Specifically, you start with some samples of a function you want to learn, some starting guess of that function, and then you perform optimization in steps until you're happy. In this talk, we'll focus on something called supervised learning, which is really these examples with input-output pairs where there's a correct label. So what does all this mean? Let's go into a little bit more detail. I have this slide. If you have to explain it in one slide, find a function that best fits some data, where data is a data set of, it's a list of input-output pairs, right? So we know the types X and Y. We don't know the implementation, but we know some input in their images out of that mysterious function we're trying to find. Of course, what best here means, we'll also get into it. But let's see some examples, right? So you've probably seen, but let's just go through some of the main ones. The main example people use is image classification. You have input-output examples of pictures of pets. You've taken images of some cats and dogs. You've labeled them, and you want to find a function that classifies new cats and new dogs and maybe new animals, depending on how you set the problem up. Other example is next character prediction. So here on the bottom, you have some sentence which says, have you run a background check? You can frame your supervised learning problem as predicting the next, in this case, not just a character, but a word. So for instance, if you input into your network, have you run a background, maybe you want to predict that the subsequent word here should be check. So many others. Protein structure prediction. For instance, you have a sequence, of molecules just in some unstructured, in some ordered list without any high-level structure or understanding of what they form, and you want to predict some high-level structure from that sequence. That is a problem that deep learning tackles with. And as a matter of fact, you've recently probably seen that AlphaFold developers have obtained a chemistry Nobel for contributions in this field. So many others, right? There's audio classification, audio generation, image generation, time series, as I said, structured data, code, and so on. Generally, we partition this into discriminative, i.e. you classify, it maps out of something, or generative models, where you produce new samples, maps into the space you're looking at. So since I'm still being paranoid, am I still on the call?
You're on. Everyone's listening attentively.
I'm just scared that I talk for 15 minutes and then I realize I'm not on.
We're going to scream when you don't. Go on.
So I've described this in a very rough sense. Deep learning has a very precise specification, precise components in it. I've described roughly the data set, but really we have also something called a loss function. This is the thing that tells us what best means, what means to best fit a data set. There is optimizers involved, and there's the neural network involved, which is arguably the most important component there. So what's the rough story, right? So if I have my image, say here, of a cat, and I'm aiming to classify this image of a cat, the way this works is that I take this image, which is a sequence of pixel values. It's these pixel values of colors. So there's a green, 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 you know, and there's some orange, then some black, etc., ordered in a particular way. One way to process this is to just put them all into a list. So each here input represents a particular pixel value encoded as a numerical value, right? So maybe we have RGB, right, which we can call red, green, and blue components of the color. And we would process these numbers in layers. We would start with some guess of some weights, which are basically numbers that multiply these inputs. And we sum them all up, apply some, let's say, activation function, some threshold that tells us whether this input is important or not, and process this in many, many, many layers. Here, there's just two. The thickness of these wires really represents perhaps the meaning or the importance of some weights, the strength by which we'll multiply the appropriate pixel value as we go on and transform it through these layers. At the end, we might get some pixel values which will represent our prediction. So maybe for this particular image, we'll say this is 70% a cat, 20% a dog, and 10% a horse. Maybe our network is not sure. The way what happens next is that we have a loss function which takes our prediction and takes our label, which is our handcrafted value, our instruction to the network in this supervised learning case, which tells us, hey, this was actually a cat. And what happens then is we produce a numerical value that tells us how close we were. So there's many ways, again, to compare predictions we make to ground truth. And I'll not go into all the details of how we can do that, but this is something called a loss function or an error function. So what happens then is this mysterious, infamous procedure of backprop, right? Where we see what the value is of the loss function at the output. And then we ask ourselves the following question. Well, if we want that loss to be lower, in what way do we have to wiggle these predictions so as to make it a little bit lower, right? So we look at the differentiable structure of this loss map. Once we find that out, we know, all right, we've got to wiggle out cat to be a little bit higher and dog to be lower, horse to be lower in numerical values. Now that we know that, we rely on the fact that the function that computed these cat, dog, and horse values was also differentiable. So we ask, how do we have to wiggle the intermediate values here so that the cat probability is a little bit higher, dog is a little bit lower, and horse is a little bit lower. Once we find that out, we go back. So we do that for all these connections here, which are called the weights. And once we do that, we basically update them. We update them as per the discovered ways of wiggling that we need to do. There's a bunch of other hyperparameters there. There's the optimizer, there's the learning rate. I won't go into all of that, but just to give you a little bit of sense of what the rough structure here is. There's been a lot of work trying to make this picture formal, and there's some ways that you can make this. So it started, to the best of my knowledge, with the paper called Backprop as Functor. Now it's been many years ago, and I've done myself a lot of work on this topic, and many other people. There's been a rise of papers in categorical machine learning, really rise comparatively in some sense. The top of this chart is 80, but I think that's a lot given where the field was 10 or so years ago. Again, this is just briefly to tell you some of this research and point you to some of the results. I will not go into the detail of all of these, but it turns out that you can model neural network as a formal construction called a parametric lens. It's a kind of a weird.
Bruno, could you just go back for a second? Could you just list off 5 names that we should of prominent people in these things besides you and Spivak, other important people in that intersection?
That's a good question. I might not say any names, but I could point you to my GitHub repo, which kind of has a list of all the relevant papers, and maybe a good way to find the most relevant people is just to kind of have a look there through the authors. I wouldn't want to single out in particular
No, that's
anyone.
perfect. That's perfect.
Yeah, yeah.
That's exactly what we wanted. That's exactly what I wanted. Okay, thank you.
No problem. Thanks for the question.
Okay.
Yeah, so I mean, you're right in saying there's been a lot of work and a lot of different perspectives. So there's just a lot of stuff happening on this front, and far too much for me to cover in really a single talk. But because what we're kind of building on and what we're trying to connect to is really a lot of that work. So in this talk, I'll just give you a very, very brief overview. I'll draw some funny pictures, but you can kind of look at that work for more detail. So there's this way of modeling neural networks as parametric lenses, right? With the idea being that, you know, your input as a cat here is an input on the left side, and instead of your morphisms as usually just having one input or one, you know, if you want to call it an input, here things are generally bidirectional because we do information propagation forward and backward. And in addition to your morphisms being bidirectional, they're also additionally parametric. So every morphism has a weight associated to it, and that weight is also updated so that we also propagate gradients back up as we compose these lenses. So, you know, you can model convolutional architectures in this way. So here we have some convol 2D, max pool, ReLU, and you can really model the entire supervised learning setting in this way. So you can compose a model with a loss, add some extra administrative things, add an optimizer, and get really an entire picture of supervised learning in a formal way using this bi-category para, and so on and so on. I've drawn a nice animation that helps me understand what deep learning is about. In terms of these components, you can really think of it formally as information being propagated through these morphisms. So since I've drawn this here very briefly again, you can think of your input, your cat, as an A, your label as a B, right? And then when you look at the way information is propagated, F consumes both, F consumes both the parameter, and A produces an output, which is consumed by a loss function to produce a loss, and then you back propagate that up and use some gradient descent map to update. Again, a lot of stuff, but if you didn't get it, don't worry. I'm just kind of putting it here for completion. The point is that we've kind of given, there is a formal picture of supervised learning, and I think it makes sense. There's not just us, but there's a few other people just working on this and building on top of this stuff, but it doesn't tackle one of the most important questions in deep learning, which is designing the architecture of the neural network, or more specifically, the structure of its forward pass. So what do I mean here by this? And I'll spend a little bit of time just trying to solidify this idea. Recall that I've talked about image processing, and I've talked about the representation of our input data. So here we have a nice cat, and we've got a sequence of pixels that we have flattened and put into our neural network to be processed and to be classified. There's one problem with this picture, or maybe not a problem, but one inefficiency that people in deep learning have figured out, have solved, and have continued to build on top of. And namely that the image contains structure. Image data contains, in this case, spatial information. We have width, we have height, and we have the color encoding, say, you know, red, green, blue. By squashing this into just a list that doesn't contain any structural information, we erase information that's useful for learning. If you want to learn well, we need structure. We need to get a grip on that structure and use it to aid the learning. What do I mean by this? Again, here's a cat, right? We often want to classify cats, and if we're doing classification, one important feature is that it doesn't matter where a cat is in the image. So maybe a cat here is in the center of the image, but maybe a cat is also on the bottom right of the image. In both cases, we want to classify this as a cat. This property of being invariant to a particular transformation of the input is going to become really relevant, because we'd like our network to be invariant, in this case, to the location of the cat in the image. So whatever subcomponent is doing the recognizing, it should kind of be applied equally across the entire image. And this is what leads us to the concept of convolution that I mentioned, really roughly represented as this filter that is being slid over the entire image and learned once, and then used to recognize different subcomponents of the image equally. So if I think about a linear layer, if I represent it as a matrix, then what I've mentioned is a convolutional layer is represented by a certain kind of a linear map given by a circulant matrix. So for instance, in this case, we see that some values in this matrix are being repeated. And that's because we want some kind of a property that once we slide the input in a particular way, the output respects that. So meaning the matrix has to transform inputs in kind of a same way across some pixels. Okay, so I was talking about structure, getting a grip on structure and important for learning. Here, this pattern of weight reuse in multiple places is called weight tying. And this is exactly what enabled this rise of image processing architectures. So structure enables learning. This weight tying, if you look back here, there's not 9 weights, but there's 3 weights now, reused in a particular way across the network. This reduces parameter count, and it enables learning and enables better sample efficiency, and really enables us to encode domain-specific priors into the architecture. So for convolution, that means that a feature has to be learned only once, and then we kind of slide over that filter across the image. Now, if you've kind of had a chance to interact, or if you've seen deep learning in practice, you've seen that there's a dozen of ways to do this. Neural networks can be autoencoders, they can be recurrent, topological, generative adversarial, autoregressive, recursive, graph neural networks, as I mentioned, convolutional neural networks. So there's lots of these. But the problem is they're all vaguely described. There's so many confounding variables. All of these architectures, half of them are special cases of each other. At least for me, when I was learning this, it was very hard. It still is to kind of get a sense of exactly what the boundaries are, exactly what's a definition of a particular kind of an architecture. So one other thing is that networks can be really huge. Am I still here, by the way?
You're here. You're perfect.
Great, fantastic. I will never not be paranoid after that.
You have there's 24 people here waiting at every word you say. Go.
Oh my goodness. Well, so one other reason why I'm kind of bringing all of this up and setting the context, because the network can be really big. We're not talking about hundreds or thousands or millions of parameters, but like, starting from hundreds of millions, from this architecture called GPT-2, it had 345 million parameters. GPT-3, kind of the precursor to ChatGPT, had 175 billion. GPT-4 has almost 2 trillion parameters. So to put this into context, that's 700 gigabytes of storage just for weights, just a bunch of numbers. I've been looking into how much this costs to train. So it actually turns out it's very hard to estimate depending on what you take into account, staffing, whether they buy or rent their compute, etc. But some estimates tell us that it costs $233 million to train. So that's just, these numbers are huge. This is completely inscrutable. Like that size of network, that amount of compute, if you fail, you do not want to fail that training run for some silly reason. You want to make sure you put that money to good use. And there is some novel some new estimates of the Grok 3 model that XAI is currently trading with estimated completion in December, that it cost $1.2 billion, or that it will cost that amount. So just absolutely staggering numbers. It's a problem because we don't understand these networks, right? We have so many issues with explainability, fairness, regulations. How do you regulate this thing? The risk model isn't even clear here. Not to mention all the problems with hallucinations, etc. And yeah, as I'm saying, these are only getting larger, these large-scale deployments. So the lofty goal of this entire program is providing a language that can help us understand existing and design new architectures. To bridge this with some existing theory of structure, there's so much interesting type theory, so much interesting logics that really are not finding their place in the field, and I think they should. So our question that we're asking, can we use any structural theory for this? And with that big introduction behind us, and the question, can we use any kind of structural theory for deep learning, I step into the second part of the talk, which is titled Geometric Deep Learning. Geometric deep learning is a subfield of deep learning, mainly developed by these authors, but many, many others as well. So this is a screenshot of a fantastic book you can read on the subject, which is a subfield that studies, in some way, stability of inputs under transformation. So it originated, if you read the book, they say originated as an application of their Erlangen program to deep learning, inspired by a lot of these study of invariants, etc., etc. And it had a theoretical and lots of practical success. These insights were used and are still being used in some ways. So when I say stability of inputs, I really mean the examples we've seen before. You've seen the image of a cat and the translation. That's one example, there's many. So to give you a sense of the kinds of things geometric deep learning studies, we can look at the previously seen example. We might want our network to be stable, not just under translation, but maybe reflection. So if we're classifying cats, it kind of shouldn't matter if we reflect the image. In both of these cases, we should get a cat. But this is applicable to many other domains. I've mentioned predicting protein structures. If we have a molecule, then rotating it should not impact the prediction of the energy of that molecule. If we're classifying some dangerous goods, etc., it does not matter if you permute the items, in this suitcase when we do the classification. And so on. And invariance is a special case of equivariance. So reflecting the cat might not give us an invariant mask, but an equivariant mask. So if you're aiming to predict, say, parts of the body of an animal and mask that part of the image appropriately, then doing a particular transformation on the input will cause us to apply an analogous transformation to the output. So again, many examples, if you're predicting, say, force fields on a molecule, then rotating the original molecule will rotate our answers, right? So we've got some kind of commutative diagram. You can see that we're starting to build into this. And again, the same thing applies for identifying dangerous objects. If we're not just classifying, but want to pinpoint which one it is, that's an example of equivariance in permutation. So as you probably know, or you might know in kind of mathematics, equivariance really means a group action homomorphism. So geometric deep learning deals a lot with group actions. It deals a lot with group action homomorphisms. So here, an action of a group G on a set X really consists of this binary operation, which takes a group element, an input X, and kind of transforms the input in a particular way as prescribed by that group element. It has to satisfy some particular laws. And as examples, we have rotation, scaling, reflection, permutation, lots of different things we can wiggle and change the input. And then a group action homomorphism really tells us that if you look at this equation, applying a particular transformation to the input and then applying our function should be the same as applying our function and then applying that transformation on the output.
Yeah.
So this is going, I'm realizing, quite fast, and I'm kind of throwing a lot of things there, but this is what, this is one way people are modeling some structure preservation in deep learning, where the transformations we do to an input data point are group actions, and maps which preserve these actions are these homomorphisms. Now, you might ask, well, Bruno, what does this have to do with neural networks? We kind of talked about equivariance, but how is that related to images? How is that related to, say, this image of cat and convolutional filters? Well, the really cool thing is that when we instantiate the concept of equivariance in the appropriate category, such as, say, the category of vector spaces and linear maps, we can represent maps as matrices. And then the equation from the slide before gives rise to an equation between matrices. And turns out when you solve that equation, you get a weight time scheme. So that's effectively, in my view, I would say limited view, the main result of geometric deep learning is that abstract notions of equivariance give us concrete equations that we need to solve that produce weight time schemes, which we can then use. Weight times are usually easy for small examples, but when things get really complex, when we're doing things on spheres, etc., we need some formalism, and that's what geometric deep learning excels at. So if you look at our paper, you might find some equations being solved for very small examples just to illustrate the idea. So, if you have a group of 1D translations, really in this, so this is, a group that contains 2 elements. It tells you either swap the pixels or not. And the induced action on, 2 pixels, then you can unpack the whole story in the category of vector spaces, get some equations now between matrices. And then once you solve it, it turns out that your matrix has to have some weights coupled. And this is what we mean by weight time. Turns out this process covers a wide array of architectures, covers group convolutional networks, graph convolutional networks, topological, and really, GDL has been a successful story. But as we're not talking about GDL here, but categorical deep learning, I want to point out a flaw of this, or a drawback of this approach, which is that we only get equivariance with respect to invertible operations. To make this a little bit more tangible, I'll get to some of the cool things that I personally find in deep learning these days. These are new and rising benchmarks that model what people are, for the lack of a better word, perhaps calling reasoning. So I'll give you some examples to illustrate this, but these are far and many in between. So one really nice example that illustrates this is called the list ops benchmark from a paper. List ops, a diagnostic data set for latent tree learning, which tells you, hey, your input will be a flattened representation of a tree, like in this picture. So, you start with a tree that has some values on nodes and leaves. So for instance, here on this node, you would have a value min, and then on leaves, you would have a value 4, 7, and so on. Actually, this tree, I'm now realizing, does not match, or in some ways matches the actual underlying structure. But you have a tree which you flatten, and you get a following string representation. The task is to take this string representation and produce a number that computes in the appropriate way the meaning of this phrase, which also has to be defined. So in this case, the minimum on 4 and 7 is 4, and the maximum of all of these numbers is 9. So you gotta compute this. Seems pretty easy, but the trick is, requires the model to process variable length input, and it requires the model to perform a dynamic amount of computation.
Could you just explain how that thing corresponds to the tree or something? Where those numbers come, max, min, 2, 9, where does that come from the diagram above it?
So
if it's
I
possible.
will be honest, it's the first time I'm matching the actual pic. I'm looking at the actual picture in a little bit more detail. I took it from their paper. But the way you should think of this is that maybe ignore the picture above for a second.
Okay.
And you should think of a tree which at its node, so tree has nodes and leaves, right? Let's think of a binary tree. I have a root node, then I have left subtree, right subtree, and then I have another node here, and it branches, etc. At nodes, I will have operations such as max or min. And then at leaves, I'll have, in this case, let's say natural numbers. So leaves will be natural numbers. I imagine you see me waving my hands.
Right.
And at nodes of the tree, right, at kind of each top of each subtree will contain, say, in this case, one of two labels, which might be max or min.
I see. So you're mimicking a tree by a string of strings, which
Well, I mean, the tree is just a parse tree for that expression.
exactly.
Yeah.
Okay. Okay. So the picture above really is nothing to do with it. Maybe.
Well, I'm realizing now that there is some brackets here, and there's it really doesn't seem to have much to do with from what I can understand. It suggests that the bracket here is matched to this branch, but then this bracket is left unaccounted for. So I'm actually realizing that this picture is very troublesome to interpret for me right now.
Okay. Okay. But
Well,
go
looks
on.
like
They
looks
only
like-
put links to the closing brackets, not to the opening brackets.
Maybe
Yeah.
that's it. Maybe
it
that's
looks like a parsing diagram where you're propagating max or min to the inner nodes all the way up until you get a result. That's what it looks like.
Yeah, I'll be honest, I find this a little bit of a confusing diagram for, I think, what might be a very simple task. But yeah, the task is the tree really is, it's an expression tree. You know, it contains an expression that contains only, say, max or min, and contains values that are natural numbers. The idea is you represent that expression sequentially in some way. And the idea is for your network to consume only this sequential representation without knowing what the tree structure is. That's the trick, right? Without knowing what the tree structure is, and then compute the answer. Does that make sense?
Yeah. Yeah. Go on.
Yeah. So turns out that's really hard to do in a way that generalizes. So you can easily build a network that works for some length, some sizes of inputs, but making that generalize for 100 times the length of an input, it turns out it's really hard. Like you can kind of build in the answer yourself, but having the network discover that by a search process ends up being problematic. So hence why people started designing these benchmarks and data sets, which kind of start tackling some more algebraic structures, some more, less geometrical, more algorithmic algebraic. So another example is, maybe you've seen the Introduction to Algorithms book, a 900-page book covering, all sorts of different things from shortest path sorting, depth or breadth first search, all sorts of dynamic programming, and many others, most of which I don't know. That was also turned into a benchmark, the CLRS algorithmic reasoning benchmark, which kind of aims to bridge the gap between kind of classical computer science and what usually is done in deep learning. So that's testing algorithmic reasoning. You kind of have to find shortest paths. You have to do all sorts of computations which are recursive in nature, which aren't invertible, which require variable length inputs, etc., etc. So all of this is really a reason why we're kind of pushing for this, and why categorical deep learning, I think, where it might have a lot of success is because the state of the art on these things, unlike some other kinds of approaches, has in many ways limited success. Neural networks can easily memorize answers, but it's hard to generalize to usually unseen lengths. And this brings me to the crux of the problem when I say that geometric deep learning cannot handle non-invertible transformations, because Steps of a recursion, if you have a recursive algorithm, each step of recursion is usually non-invertible. If you have an automaton or a dynamical system, transition functions are usually non-invertible. Aggregation steps of dynamic programming algorithms, say, you got to sum up all the nodes or you got to take a max, that's usually a non-invertible functions. Not to mention that programs which read from some memory or write to memory also are not invertible in general. So the question we kind of pose in our paper is, how do we bridge this formalism? How do we bridge the formalism of equivariance with data types, general algorithms, branching, and lots of other concepts from computer science?
Right. This is why monoidal actions were big in computer science, not group actions.
Right, because monoids don't assume invertibility.
Right.
Or
Yeah,
in or in some classical settings, this was the motivation for the introduction of inverse semigroups as well. So like rigid motions in a fixed size image, if I've got a hand here versus my hand off the screen, there's a partial inversion where I've deleted this part of my hand. We come back, that's an inverse semigroup. More generally, these are actions of simplicial groups on simplicial sets, where you capture the bookkeeping of how much of the image you're actually inverting.
Oh, that's interesting. I haven't heard of these, I'll admit. I'm sure there's many, and that's exactly, I think, where we're going with this. Because
yeah, I don't mean to derail. It was just two
no,
references, inverse semigroups and these actions on simplicial sets.
I think this is exactly the point of, you've already latched on to the main idea. And when I tell you what we've done, if you haven't had a chance to look at the paper, in many ways, the answer will be very underwhelming. It's a very simple thing. We say, well, okay, we can go from group actions to monoid actions. Monoid actions are algebras. Why don't we study categories of algebras? That's it, right? But let's see what that means, right? So categorical deep learning, I usually say it looks like this. Instead of just training your neural network in some framework, you kind of do all these extra steps and come back to a very simple realization. That's what we're going to do right now, and you have no choice. So Noston, you were completely right. Like we a lot of the times we want to do a monoid action, and when we are doing group actions, really a nice way to see it categorically is in the sense of an algebra for the group action monad. And the map that preserves these actions is an algebra homomorphism. Meaning that, our morphism x f from x to y is really, it's equivariant if this diagram commutes, and it's invariant if the diagram on the right commutes. So here the difference is, right, we've got a projection here as the action. So as I've said, you've already latched on. It might be very, it might seem like a trivial step, but it's one that captures the idea of equivariance perfectly and allows us to generalize in the right way, right? G only needs to be a monoid for G times blank to be a monad. And we really did not need a monad to begin with. Turns out, you can define endofunctor algebras as well. So if you study the endofunctor 1 plus a times blank, say on set, then you can, the set list A together with the map 1 plus a times list A into list A is an algebra of this endofunctor. Turns out this algebra is special one. It's a special one. It is the initial algebra. So you can use this. You can use maps out of this algebra. So if you've got another one, goes 1 plus a times x into x, then there is always a unique map from list A into x, which is an algebra homomorphism, meaning it is a fold over a list. So you will take a list of inputs and you will fold over them. You will apply some little cell that is iterated recursively. Many similar endofunctors exist, as you know. I kind of maybe don't spend too much time in the sense of slides here, but what we do in this paper is unpack what all of these things mean. So we take all of this stuff, that people know in category theory, and for the machine learning audience, we say, hey, the thing that you are calling a recursive neural network, I think that's a particularly bad name, but recursive means it consumes a tree effectively, and it folds over that tree. Well, we say, okay, actually, all along you were studying a particular initial algebra of the endofunctor a plus blank squared. So actually, what I've said before is really maybe more nicely here on a slide, where the list algebra here is initial, and for any other algebra into X or into any object, there's a unique map FR, which is structural in nature. It's implemented with recursion, and that's, so it means that F applied to the empty list has to give us the result of whatever R0 is applied on the one element set, and then applying F on a cons has to be the same as whatever ends up being here R1 of etc. etc. The same story applies with trees. It's the same principle. Any recursion pattern you might have seen. This is well known and well studied in category theory. What we've really done is say, hey, actually, a lot of these concepts that appear in deep learning that are called in different names, you can study them through this principle. So categorical deep learning, we dualize the entire story. You can study coalgebras. You can get streams, you can get Mealy machines. These are all things that you might have seen. I won't spend too much time with this because I'm also realizing we're kind of getting towards the end. But I'll say one thing, which was that what I didn't know, when we figured out, oh my God, it's kind of all algebras and initial or final, initial algebras or final coalgebras. I went and tried to unpack as many as I could that makes sense. So it turns out you can unpack a few of them, for 1 plus a times blank, you get kind of folding networks. You can also study coalgebras for the product, you get unfolding networks. Then for the trees, you get recursive neural networks, as I mentioned. And I was really wondering what happens when you do the Mealy machines, right? So there's a coalgebra, there's an endofunctor whose final coalgebra describes Mealy machines. And I was really wondering what happens when you do the iteration there. It turns out you get exactly recurrent neural networks. That was very novel to me. After discovering this, I looked up, and people have studied this in the literature. They've found this correspondence, but not in a formal way. It's kind of, or at least not in a formal way by the category theory standards. So that's been a pretty fun thing for me to learn, that there is a correspondence between parametric Mealy machines and recurrent neural networks.
Well, Bruno, what category are these coalgebras in?
So that's a good question.
Thank you.
That's a great question, and you've spotted me kind of putting that under the rug. So the first answer might be the category of vector spaces. But so the answer is, for many of these we know, but for some of them it's a little bit unclear how to compute this exactly. So the answer, I think, on a shallow level is the category of vector spaces and linear maps. So for instance, if you unpack an unfolding recurrent neural network, you need O times blank, right? You can really just take I actually don't remember whether you have to take the tensor or the byproduct, but one of them works. For some of these, you get into slight problems because you gotta start taking care of. You're working internally into a category. So if you're working in vector spaces, you gotta be careful about what it means when you say plus and what it means when you say times. We go slightly into our paper, but I would say it's not abundantly clear how to solve this without doing some more syntactic. I'll actually get to this when I mention some factorial constructions, but that's a really good question. I don't know if that answers it.
Well, I just want to understand a little bit better what was the issue you were saying? I don't think I understood that. What's the problem?
So if we work inside set, when I write the endofunctor 1 plus a times blank, times means the product in set, the Cartesian product of sets, and plus means disjoint union, right?
Mm-hmm.
And set has initial algebras, and a key component of you being to show this end of function in set has initial algebras is the fact that you can distribute plus over times or times over plus.
Okay.
Now, when we go and try to interpret this category, this diagram or this end of functor in the category of vector spaces, we would have to pick some vector space A, which is not a problem. We would have to pick 1, but now we have to ask the question, well, what is 1? Is that R0? Is that R? Is that the unit for product? Okay, maybe it's the unit for the product. Okay, are we using a product here? Okay, but then if we use a product, plus will be the same structure. There will be no distributivity law, right?
Okay.
So if you're in vector spaces, you got to take some care, and you have to say that so what I'm effectively saying is you have to be careful about how you interpret this. In vector spaces, instead of times, you will use the tensor product, and instead of plus, you will use the byproduct.
Okay, but there exists some interpretation of it such that this matches what's in the literature.
Yes.
Okay, cool.
Yeah.
Thank you.
Right, you're just saying that that interpretation is not automatic, and you may need to think in each example what is the correct way of interpreting a thing categorically.
Yes, exactly. And this is the part where actually we haven't done all the formal proofs. This is a machine learning conference, so we kind of hand waved some of these things, but a lot of these things remain to be fully unpacked in a lot of detail that I think would make me satisfied, and probably you as well.
So I mean, it doesn't work in the category of sets. So can you make some type of statement about that? You can't do neural nets in sets, or is the things too complicated?
Well, so the whole story works in set, and this is well understood inside the category of sets. The only problem with set is that you do not assume that the functions at hand are differentiable. And for these to be, in some sense, neural networks, you want the morphisms to have some, the category to have some differentiable structure on it. So set does not have one. So the whole thing works in set, but you do not want set really.
Right, it's too trivial. The whole point of what you were saying is you want to have some structure that you could use. Set means you have no structure.
Yeah.
Can I just say, classical computers can be mimicked by sets or sets of states. Quantum computers need vector spaces, Hilbert spaces, things like that. That's just a side point. So, yeah, I'm just saying that just as interesting as what you're saying. Go on.
Yeah, so I'll actually mention a little bit in future work some interesting aspects I think related to what I think might provide a really satisfying answer to some of these questions. But I think for now I would say we work in vector spaces with these caveats that I've mentioned. But yeah, the whole story is, you can unpack, there's the Moore machine and the function as well. You can unpack what those are. Turns out that's something I've never seen before, but I also think it's not something that's really useful. It's a kind of a recurrent neural network that does some weird copying and doesn't have some dependence. Not really useful, but you can do it. And so yeah, by the way, part of what I'll actually say, what I forgot maybe to say as one central bit is that what we wrote is a position paper. ICML this year had for the first time a position paper track, which is a track that's whose contributions are supposed to advocate for a particular perspective, advocate for some things to be done, etc., and doesn't necessarily need to conduct a lot of novel research. And that's exactly where this fits. I think a lot of these high-level categorical stuff we really want to do and really check all of these things in detail. That's TBD. part of what we posit and show in this paper is really this two category of parametric functions as well, which we think is essential in modeling some of the things that people in deep learning kind of found and kind of discovered, but don't talk about in these ways in a formal way that we, I think, with CT can. So the idea is that when you compose two neural networks, say neural networks that have linear maps on them, if I compose a linear map with an activation function and a nonlinear map, the composite will not be a linear map. And often people model this as, say, just a smooth map. And that's fine. But it ignores one important aspect of neural networks is that we often store and represent these as just pairs of matrices, right? We store the parameter of this neural network as pairs of, or for an arbitrarily long neural network, as a sequence of matrices. So we want our morphisms to carry some additional pieces of data, allowing us to kind of get a grip on these parameters that go into the network. So to that end, there is this category para defined numerous times in numerous settings, whose objects are sets, and morphisms are parametric functions. So that means a morphism from A to B is a choice of a parameter P, where this is an object in set, and then F, which is a function of type P times A into B. Turns out this is it's not just a category, it's a two category, or actually, if you're being really careful about associating things, it really ends up being a bicategory. People have found, it's a double category, so you can make it more formal. But the main idea is, to my mind, that it's captured in the picture below. So when you compose a parametric morphism from A to B and one from B to C, you will chain the computations like this, but you will tensor the parameters. You'll put them in parallel here. So this is also something we advocate for in the paper, and we show that the weight sharing ends up being modeled by two cells in this category. So I have some pictures. You can maybe look at the paper for a little bit more detail. I don't know if I have the picture here, but the weight sharing is actual explicit copying, right? So when you have one weight and you use it in two places, you explicitly copy it. And this is exactly how people in deep learning frameworks, at least the modern and new ones, such as JAX, model. Like, you explicitly have to be functional in the parameters. You copy them, and then when you propagate gradients backward, you sum them. So we advocate for this to be modeled via, this is some construction that could be used to model these very implicit things in deep learning, in some more formal way. So I've talked a lot. I'm realizing it's been 1 hour. I'll the main concept, I think, for me is that we can put some formal connections between things people talk about in deep learning and our categorical principles. This is a position paper. You're rightfully pointing out, like, hey, what about this? How do you do that? There's many things that are unknown, and I think this is what we hope to, or maybe inspire, or do the research ourselves, to talk about structural recursion, to talk about networks that process not just arrays, but that process, when you write programs, right, you have inductive data types, you have co-inductive data types, you talk about pattern matching, you talk about types. In neural networks, it's all arrays. So we hope to kind of add some of these structural primitives into deep learning. So having said that, I will briefly say what the future work is in a few minutes, and then maybe I will stop for questions. Future work, I've realized or discovered this piece of work that models dynamic programming using a generalization of both initial algebras and final coalgebras. Turns out you can generalize both in the same ways, called, you do that using recursive coalgebras. And that found to me the coolest description of dynamic programming, which is a coalgebra to algebra morphism. So you say algorithm from P to S, which solves a problem P into S, is a dynamic programming algorithm if this diagram commutes, where you have some coalgebra map telling you how you break your problem into subproblems, you solve the subproblems recursively, and then you combine the solutions. something that people haven't really modeled in deep learning. I'd love to see how all of this structure, all of this weight sharing unpacks here, whether we can say anything interesting.
Okay, well, do you have someone, a name that fits with this, that did dynamical programming like this?
Yes. So I have to remember what the there's literally, yeah. I'll actually find. I'll look up the paper and tell you. But there is the
Okay.
paper that models dynamic programming using this way and unpacks all of this in more detail. Oh yes, it's called Recursion Schemes for Dynamic Programming. Yeah, so this is Kabanov is the author.
Kabanov and Vene, V-E-N-E. Perfect.
Yeah.
Thank you.
This is where I really got this idea from. They unpack it there. It's really, the connection is established in that paper, and not really mine. I'm just saying it as an application. Yeah. Thanks for the question. It's good to have references. So one other thing we'd love to explore is, deeper exploration of functorial semantics. So G equivariant maps can be modeled via functors from BG into set, where B here is the looping of the group. And so we think of it as a one object category. There's interesting research to be done, kind of phrasing all of this stuff we talked about in this way as well. And to end, I'll talk about something that's perhaps the most exciting to me, which is this idea of automatic alignment. This tells us that the prevalent paradigm of machine learning, in which we bake in priors ourselves, we've seen that earlier in the talk, where we look at the network, we choose circle and matrices, we choose some weight tying, we bake these priors in ourselves. This is called manual alignment, and there's new evidence pointing a change in neural network architectures that require us to manually align them to the domain-specific priors into ones that do it automatically. So again, what do I mean? Manual alignment is procedure of aligning the structure of the network to a particular domain of interest by manually looking for the structure in our domain data, and then manually tying or coupling the weights in neural network layers so that the network becomes a homomorphism of the structure we discovered. This is great, but it's error prone. It requires us to do it. It's manual in that sense. We got to do a lot of work for each different domain. It's hard to translate this across domains in a systematic way. So convnets are an example. People have noticed that the data lies on orbits of a group action of translations and have tied the weights appropriately. Recursive neural networks are another example. But many novel architectures challenge this assumption, and specifically the most interesting one is being the transformers, and specifically the attention module inside of it. So there is fantastic new research, really, really recent, showing us that there's ways that you can set up an architecture which learns some equivariance properties from data. So the most notable example is the architecture of vision transformers, which in most of the architecture does not contain any convolutions or any obvious built-in knowledge about groups or orbits or weight tying in the way that you would imagine. But showing the network data that lies on orbits of group actions of translations causes the result of the trained network to become equivariant to the group of translations. If you show the network images that lie on the orbits of group actions of rotation, then the trained network will become a homomorphism of that structure. So it will be invariant to the translation. So it's really interesting. I have no idea really how this works, but attention seems to be a key component in this. And really, as we've seen with interacting with ChatGPT, it might be one of the reasons why it kind of learns on the fly and does all of these cool things. So the trick is we can learn some equivariances, but not others. Transformers notoriously don't do structural recursion really well. They learn it up to a certain depth and then fail onwards, and so on and so on. So a lot of this research is position paper, but we hope that it helps us understand some of these key issues of what it means to learn, and some of these key issues of what it means to tackle structure, to get a good understanding of what structure really is. So in that sense, I'll leave you with this fuzzy thought, with this conjecture, that there is some deeper correspondence between what you might call the aim of deep learning and the kinds of results that we see by applying category theoretic principles. Well, you know, when we do category theory, when I do category theory, there is some set of implicit principles that I follow, that you might have followed. And as a community, category theorists have found common abstractions across different scientific fields. There's some of these principles that we follow, and there's these common patterns that permeate different fields that I was surprised to see, and probably you as well. And in deep learning, we're trying to build in networks that look at data and find general patterns in data. We want to find patterns that are composable and generalizable, but deep learning is looking for this theoretical finding and for these set of principles that would allow it to, allow neural networks to learn from data in a more efficient way. So I hope, and I think we might see some interesting correspondences down the line as we continue tackling what it means to learn, what it means to grow structure. But at the point, it's kind of unclear. So I kind of leave you with this relatively vague thought. And yeah, there's so much deep learning we can do inspired by programming language theory, add structural recursion, dependent types, so many interesting things. I think we'll keep seeing more of that. And this is where I'll end.
Sorry. Thank you very much. It was an excellent talk. Any questions?
Yeah, I have a question. So first of all, great talk, Bruno. Could you go back to the slide where you were talking about like two cells passing the weights or something? Yeah, the next slide. Okay, so can you say a little bit more about this slide?
So what we see here are, on the left, what you might call a recursive neural network. And on the right, I don't think it really has a name. It's this novel thing that you might come up by looking at some category theory. So I'll focus on the thing on the left. On the left, we see a neural network that processes, in this case, inputs of type A, which will represent the leaves of our tree. So it will process an arbitrary number of inputs let me put it this way. It will process a tree whose labels on leaves, so this will be the leaves of the tree, will be labeled by A. So on leaves, it will have something of type A. Depending on the tree structure, we want to fold in such a way that our neural network, when it produces the output of type X, respects that tree structure. So what we really need to define in this case, since this is a binary tree, actually you can see that each node has two subtrees. We need to define, in this case, a map x times x into x and a map from A into x. Once we define these things, our recursive neural network, i.e. the one that processes trees, is defined to be the one which repeats its cell, which is this map that we defined, appropriately in such a way that it matches the tree structure. And since this map is parametric, it will be specified to reuse the same parameter across the entire subtree. So here, by the way, the second axis, the ones that's vertical, represents a parameter coming in. And the specification of our recursive neural network states that you want to reuse the same parameter value across the entire subtree, across each location in the tree. So your invariant really where you are in the tree, you know you will fold over it with the same function. What's drawn in this picture is one depiction of such a neural network. And what kind of you can't really see here is the explicit two-cell, at least it's not really neatly defined, but it points to the following idea that if you have a neural network that has two inputs, two parameter values, you can model weight sharing, the copying of the weights, by copying the parameter value appropriately into each input. And that's what the picture here kind of models, with some, I would say, artistic choices about how to structure the copyings.
Okay, I think I understand more now. So let me just see if I understand. So each point there, like you have A and X. So these are morphisms in para, and then a two cell is a map between the parameters. So then what you're doing is that you're like copying all the parameters using two cells, and then you're getting another big diagram in para. Is that right?
Yes, that's right.
Okay, cool. Thank you.
Any more questions? Bruno, I have a complaint against the first slide where you say we're not talking about Liouville algebraic theories, because in some sense, when you're reconstructing an algebraic theory from the category of algebras, you're looking at invariances. You're looking at could be non-invertible invariances. So this does go back. I mean, I'm not complaining, whatever. I'm just saying, this is. I mean, you mentioned it again, functorial semantics. This is what functorial semantics is all about.
I completely take your complaint on board. What I meant to say is that we're not talking about them explicitly.
Right.
In the paper, we actually make some connections and make some of this a little bit more tangible. But when I was talking about this here, I wasn't talking about functors from BG into set. I wasn't talking about the syntax and semantics. I was kind of talking about categories of algebras. But you're right in saying, to my limited understanding, that there is a way to make these connections more formal. Yeah. If that's what you were saying.
Right. No. I mean, whatever. It's a beautiful topic, even if you never mention algebraic theories. But algebraic theories reconstructs the theory. I mean, you can reconstruct the theory by looking at the category of algebras. You're reconstructing the type of type of network that you want based on the symmetries that you want it to satisfy, or invariants that you want it to satisfy. Anyways, absolutely fascinating. Anyways, thank you. Any more questions, discussions?
I have a vague question, actually. So I'm really curious about this idea of learning algebraic structure and I guess learning symmetry, learning equivariance. Can you say more about how that might work? Like if you're presented like data, if a neural net has a bunch of data, like learning grammar, maybe, like if you're presented like a sequence of symbols that are categorized by various types, and you want to sort of in the space of all like context-free grammars, like what's the one that best fits this data set? Like, can this be used to do that, like rather than the other way, like imposing some equivariance but trying to like detect the algebraic theory itself,
Thanks for the question. Yeah, the question makes sense, and I'm wondering how to answer it. The quick answer is that I don't think mechanistic interpretability of the learned equivariance is really well understood. That's my take. There are limited results on learning in the literature. There are limited results on learning certain kinds of structure. But to my understanding, these results are often very specific very
Right.
specific. Often they really assume, you have to have groups. You do Lie groups. You do some really
Sure.
specific structure to that. But when it comes to like more complex grammars, I think this is a really hot topic of research that has been underappreciated by kind of the structural community. A lot of the things that could be done there, I don't
Yeah.
think.
I mean, like, I'm just thinking, like, one, like, very naive thing that comes up is that these structures kind of live in a discrete space. So how could you use differentiability to, like, optimize, you know? Like, I guess you could take probability distributions or something and then try to optimize, but
Yeah, I suppose that's the main question, right? When we do learning, when we do optimization, we do it clearly in some smooth, continuous way, but clearly inside our brains, we're doing some structured, discrete algebraic manipulations.
right.
And I think that's the question of how to bridge the gap between algebraic and continuous here,
Yeah.
in a way where you backprop through the structure, but you kind of still do these algebraic manipulations, or you learn them at the same time.
Yeah, like are there any examples like in very, very simple cases, like say, because I don't really know too much about the machine learning world, but like, I don't know, learning symmetry, like if I train a neural net to like, you know, whatever, some kind of like neural net on images, and I train it in such a way that the data I show it is you know, the training data is like has symmetry. Like, are there neural nets that can like detect symmetry? That'd be like, even in a very simple case, like a subgroup of like just cyclic rotation group actions or something. Like, oh, this has threefold symmetry, you know, things like that.
Yeah, I think there are, and I remember seeing a bunch of different work on that front. But I can't at the moment recall any of the details of how they did it, or maybe point to. I can maybe have a look and figure out if I can say something more. But yeah, there's some stuff I think I've seen on that front.
Cool. Okay, cool. Yeah, I was just curious. Thanks.
Anyways, if there's no other questions, let's just thank the speaker again. Anyways, Bruno, thank you. Fascinating. Very interesting topic. Very interesting stuff. I just want to say next week we're having David Jazz Myers is going to talk about Tontextad's para and Kleisli constructions as wreath products. You're all welcome to come. I don't know yet exactly when, but anyways, thank you, Bruno, and you're going to keep us busy for the next 3 weeks or so, for a long time, with all those papers and things we have to learn to be part of the world. Anyways,
Thank you so much for inviting me. It's been a pleasure.
Okay, thank you very much. Okay, everyone, have a great day. Take care.
Bye bye.